In this video, you will see some special cases with three variable systems. So here's a system that looks just like the systems we've been working with. And we're going to proceed as usual. I'm going to make my table. And I'm going to first eliminate this 2x. So let's rewrite the first and the last equations. And we can eliminate that 2x using either the first or the third equation. We can multiply either one by -2. I think I'm going to go with the top equation, but it really doesn't matter. So on the side I'll have -2x plus 6y minus 2z equals -2. Copying the second equation. We add those together. This is gone. We have 5y minus 4z equals 0. So we're going to put that right in. 5y minus 4z equals 0. Okay, next step, we're going to eliminate this x right here. So let's rewrite the first and second. And we can eliminate that x by multiplying the top equation by -1. So we get -x plus 3y minus z equals -1. Add those together. X's eliminate. 5y, sloppy 5, let's try that again. 5y minus 4z equals -2. So that's going to go right here. 5y minus 4z equals -2. Okay. Now, we move on to eliminate the 5y. So we rewrite the first and the second, and we see that we can multiply really either equation by -1, but we conveniently have 5's here. -5y plus 4z equals 0. And when we add these together, these cancel like we planned, but then notice that the 4z's also cancel. We get 0, 0 on the left side, and on the right side we get -2. Now 0 is most definitely not equal to -2. And just like when we were working with two variable systems, this tells us that this is an inconsistent system. That is, there is no solution. So if while you're working on a three variable system, you end up with a false statement, you know that your system is inconsistent and has no solution. So here's a second system. We're going to make our table, and this one conveniently has doesn't have an x here in the second row. So the first thing I'm going to do is eliminate the x in the third row. So we rewrite first equation and the second equation. And this looks nice because all we have to do is add the first and the third equations together. So we add those, the x's are gone. We've got 3y minus 3z equals 0. So let's write that in our third row. 3y minus 3z equals 0. But now we're going to eliminate that 3y. So we're rewriting first and second. And in order to eliminate the 3y, let's use that second row, and we're going to multiply the second row by -3. So we've got -3y plus 3z equals 0, and the third row is 3y minus 3z equals 0, and you might already be noticing that everything cancels out. We've got 0 equals 0. Now that's different than the previous problem because this statement here is true. So this is not inconsistent, it's actually consistent. And in fact, it has infinitely many solutions. So if you get a false statement here, we have no solutions, and if it's a true statement, we have infinitely many solutions. Now there actually is a way that we can list those infinitely many solutions. The way we do this is we let z be equal to a. That's always your first step. We're just going to let z be equal to a. And you can really make this any other letter in your alphabet. You can make it b, you can use your first initial, whatever it is. But we're going to use a to represent z. So if z is equal to a, well, we know that y minus z is equal to 0 from this second row right here. So that means that y is equal to a. So in this case, z is a and y is a, so z and y are equal. Solving for x, we have x plus y minus 3z equals negative 1, which means that x minus 2a equals negative 1. So all of our x's will be of the form 2a minus 1. So this is what all the solutions look like. They're all 2a minus 1, a. So this is representing infinitely many solutions here, but we could list a couple specifically, and we do that by just choosing a value for a. So we can say that a is, let's say, 7. So if a is 7, z is 7, y is 7, and then x would be 2 times 7, which is 14, minus 1, which is 13. So that's 1 point in our solution, and you could check that by substituting that back into the original equations. If we wanted to list another one, maybe we could go with negative 1. If a is negative 1, z is negative 1, y is negative 1, and then x would be 2 times negative 1, which is negative 2, minus 1, which is negative 3. So this is yet another one of our infinitely many solutions. So this is how we represent those infinitely many solutions, and these are just a few of those specifically. Okay, here is our summary. In both cases, your variables cancel out. In the first case, if your variables cancel and you're left with a false statement, that is something like 0 being equal to 2, something we know that isn't true, then your system is inconsistent and has no solution. But if your variables cancel and you're left with a true statement, that is instead you get 2 equals 2, or I think we had 0 equals 0, something that is true, then your system has infinitely many solutions. But you have an additional step here. You're going to let z equal a, and then you solve for x of x and y in terms of a.